Hello everyone. Today I'm going to showcase a Python-based blockchain that I've been working on for the past couple weeks. And I'm going to discuss the why this was created. I'm also going to showcase the actual code in GitHub. And then I'm going to run this in PyCharm so you guys can see how this works, and we'll hit certain breakpoints. And then after that, I'm going to wrap up by discussing the next steps and what comes next in order to keep this going. So let's go to the GitHub. And to understand the why, really I want to showcase the README, right? So this project, I call it Decoupled, right? And the reason why this is important is because other blockchains, pretty much every blockchain that I've seen is strongly coupled to the fiat system. And I think one of the main problems that we have is that even though Bitcoin is revolutionary and does a really great job as acting as a commodity, unfortunately, it is strongly coupled to the fiat system. So what do I mean by that? Strongly coupled meaning that when fiat goes up, Bitcoin goes up. When fiat goes down, Bitcoin goes down. So think about this, right? When it comes to cryptocurrency, the purpose was or is to have an alternative. But if the cryptocurrency is always linked to fiat, then it's not really an alternative, right? So the idea behind something which is decoupled is to have a system that, yes, it acts as a cryptocurrency, but at the same time, you cannot inject large amounts of fiat money into that system. So I'm going to kind of discuss this more, not in this video, but I have different strategies that I'm going to try in order to keep this particular blockchain decoupled and fiat free. So fiat free meaning that the influence of pre-existing fiat will not have a strong impact on the system, right? So that's really like the big problem that exists. Now, another question is why Python? So I think Python is a really great language. It's very simple. Python has that whole idea of Pythonic, and that's something that I really vibe with, right? And again, I was like, why not? Why not make a Python-based blockchain? We have something which is written with the Ethereum virtual machine, right? So it's kind of based on JavaScript, and it works very well. One of the things that I want to solve with this is to make a system which is simple, because Ethereum is quite complex. And when I say complex, I mean it has too much going on. Bitcoin's actually a little bit better because it's simpler. But even so, I think it could be simpler, right? And one of the ways of making this simpler is to make sure that the code itself, the underlying code which run these systems, make sure that that code is very simple and very readable. So hence, that's why this is created. As I mentioned here, the code is very much unfinished and untested. This is kind of just like a lightweight version. I am strongly considering making a closed source version of this. This closed source version may be more tested and have a little bit more features. So, as I mentioned, the reason why it's called decoupled is because it is decoupled from the fiat system. And this kind of discusses how to run it. So the first step is to install the requirements, and that's a simple pip install requirements.txt, right? And then after that, you want to create the flat database files. So this system, this blockchain system, is run in two databases. The first database contains the actual blockchain data, and that's called blockdb. And then the second database contains the amounts. So this contains information that is not so much based on the past information. So the difference between the two is that blockchain, you're continuing to build blocks as you go, right? And that gets larger and larger. And the pre-existing block is built on the previous block. So the state database, I made this separate and distinct because this is simply the amounts, like how much token a public key has. That's really why I made it. And also I made it because sometimes you may want to access the state DB and you want to access it very quickly without needing to access the block DB. So once you have created these files by doing touch you can then run the server, right? So this is a blockchain server, and I'm going to dive into the code and kind of show you how this works. Simply put, you run Python masternode main.py. All right, so let's get into it. This is my PyCharm editor, and let's look at that code. So here, this code is broken down into various folders. You have common, masternode, miner, and UI. Right now, the UI is really empty. There's a placeholder file that I have. Ultimately, I want to make it so you can actually do mining and transactions through your web browser. And that's not finished yet. Miner. So miner is what you can use to mine token. In order for the miner to work, it has to communicate with a master node. So before you run the mine code, you want to run the master node code. And the way how the system works is going to kind of, describe this. It's kind of like, it's very similar to a blockchain called Arbitrum. And in Arbitrum, you have kind of like a centralized node called a sequencer. And this is the facilitator for a lot of those transactions. So this is very similar to that, where you have one master node that's acting, and it's kind of facilitating all those transactions which are happening. So let's take a look at that code. I'm going to open up the master node folder. And here you see that we have the blockdb and the statedb. These files are being ignored. So, like as your blockchain grows, you don't have to worry about committing that code to GitHub. All right. So the most important file here is called servdb. And this is essentially a web server that is run via Tornado. So it's using the Tornado web framework. And it has really two different endpoints that are working. It has one for unmined blocks. So this is what you use to interact with unmined blocks. In particular, you can get an unmined block, and then you can also mine an unmined block, right? So when you post to an unmined block, you're actually mining. And I'll show you how that works. And then the second is a health check. Health check is more like a ping. Excuse me. Health check is an endpoint that you would use to ping to see if the server is working or not. And then we have another endpoint, which again doesn't work because I haven't made this yet. And this is for transactions. The whole point of this is that you can actually do transactions. You can actually post transactions to the server from your web browser. And it doesn't work, but eventually it will. Another thing that you can do with this endpoint is that you should be able to get a list of transactions that have actually occurred. All right, so let's keep on going. Let's look at the unmined block. So as I mentioned, you can do two different methods with this. So you first have the get method, and this gets the current unmined block. So it's very straightforward, actually. So what this does is that it gets the blockchain, and there's a blockchain instance that's actually instantiated before this, and I can show you where that is in just one moment. So it gets a blockchain, and then it gets the unmined block. Now, if this unmined block exists, then it will render that block as a dictionary, and then just write that block so you can see the contents, right? That's how it works. If it doesn't exist, the data is going to be none. So let's say that there's a block that's unmined, right? The first miner to mine that block will get some token. And once it happens, once that block is mined, then unmined block is going to be set to false. And then the next person that tries to mine it will get data is none. And then see that, hey, there's no unmined block. So that's how that works. And let's dive into the blockchain instance. So as you see here, what's happening is that this starts off by creating a blockchain. And if you want to see the actual code that I use for the blockchain, you can actually go to the common folder and you'll see that that's being imported. By the way, what's cool here is that I'm using specific import to handle the imports. Specific import is something that I created because I wanted to make it easier to import files within Python. So let's take a look at the blockchain, because there's actually a lot going on there. So go here, and this is the blockchain helper code. So the first thing that it does is that you kind of initialize a whole bunch of constants here. So here you have the location of constants. You have block, which is a helper that's coming from the common folder. Let me expand that so you can kind of see. So in the common folder, we have block, and block is the definition of a single block. So remember, blockchain is really a collection of blocks, and block is just one block. So I'm going to start off by looking at block, because I think that is the simplest thing that you can look at here. So every single block, and let me move this down so you can kind of see more. So every single block consists of a set collection of information. The first thing is an index, and the index is that block's position in that global blockchain. So let's say your blockchain has like 100 blocks. The index would be the position in that blockchain. As your blockchain grows, the index that you have or can have will increase. Nonce. So the nonce is actually used to find the proof for the blockchain. So the proof is what you use to do the mining. And long story short, whenever the blockchain is mined, you're taking a hash of that blockchain, and then you're taking the nonce, and then if that hash that you have with a certain nonce starts with 0, then it's going to be a valid hash. And then you can say, okay, this proof is correct. Otherwise, if you have a nonce and then you take the hash of that with the blockchain information and it doesn't start with a 0, then you have to get another one. You keep on doing that until you find a valid proof. The next thing would be transactions. So every single block that exists has a series of transactions. And simply put, a transaction is really a list of like objects, like dictionaries, right? And this is the part that I'm not quite finished with yet. That's something that I'm going to work on. Also, every single block has an end timestamp. So what happens is each block is valid for some period of time. So arbitrarily, I chose this to be 60 seconds. So each block will last 1 minute. What does that mean? So that means that all the transactions that are posted to the blockchain for 1 minute will end up in a particular block. So that's what that means. So after the end timestamps has occurred, all those transactions that occur will be in the next block. And then previous hash. So every single block references the hash of the previous block, and that's what this means. Scrolling down, we have hash. So hash represents the hash of all of the transactions. So let's say that you have like 100 transactions or 1 million transactions in that particular block. In order to kind of represent all of that information in one thing, the hash is taken off that. And then that's what this is equal to. Difficulty. So difficulty is used for mining. The higher the difficulty, the harder it is to get a valid proof. Now remember how I said that when you're getting a proof, you have to look, the way how I wrote this code is that a proof is really a hash, and it's valid when the first character starts with a 0. So what happens is when the difficulty is increased, that 0 is offset, so it's harder to get that 0. And simply put, it takes more iterations or more tries to get a valid hash. And then what else do we have here? So we have metadata. So meta is essentially, this is metadata, which is information that I think is important, but I didn't want to store in the blockchain. So if you look here, essentially right now there's only like one thing that I care about, and this is whether the block has been mined. And you'll see why this is important later. But simply put, it matters whether the block is mined or not. If the block is mined, then we can move on and start storing transactions in the next block. If the block is not mined, then we can continue storing transactions in that particular block. And at the same time, the reason why I don't want to store this information, and this has the block been mined within the block itself, is because it's kind of redundant. You don't really need to store that. By the time this block has been stored in the blockchain, it's always going to be true that the block has been mined. So that's why that is stored as metadata. Now, scrolling down here, I want to show you guys something. When this block object is rendered as a dictionary, you'll see that it actually removes the metadata. So that is actually tossed away. And it's done because I don't want to store that, right? So that's where that metadata is being deleted. All right, so let's see, what else do we have with block? So within the block, we have the ability to compute the hash. And as mentioned before, the way how the hash is created is that we'll take the dictionary. So we're going to render that entire block as a dictionary, right? And then we're going to take the nonce, which is the integer that I mentioned before. And then after that, we will create a string based on that. The reason why you need to create a string is because in order to find the hash, you need a string. You can't do the hash on a dictionary, right? So we take the string and then we turn that into bytes, and then we take the hash of that. And then that's what we have as a hash. So this particular function, it doesn't care whether it's a valid hash or not. All it does is give you a hash off the block. That's all it does. So that is the code for one single block. And remember, a blockchain consists of many blocks. So let's look at the blockchain code. From the high level, the goal of this blockchain code is to keep an account of all the transactions that have occurred in the past. So it's to essentially hold on to the blockchain history. And then also we want to look at the token amounts. And then also the third functionality of this is to keep track of any unmined block data. All right, so let's take a look at the instantiation of a blockchain. So every single blockchain, the input that is passed is the seconds between blocks. So if you recall, when it comes to blockchain, this is an arbitrary number. If you wanted to, you can make it 5 seconds. You can make it a second. I thought 60 seconds would be good for the beginning because I don't think many transactions will be posted to this. And then here you have a default difficulty, which is just 1. You have the block tables, which, as I mentioned, these are flat files. You have active. So this is active, meaning that the blockchain is active. Scrolling down, here we have the actual chain itself. So here you have the blockchain, which is a list of blocks. In the very beginning, this is instantiated as just like an empty array. In the very beginning, you have the index. The very first block will have an index of 0. And that's what this is for. And that particular block will have unmined transactions, which is going to be a list of dictionaries. And because in the beginning you start off with nothing, you have an empty list. Oh yeah, and this is really important. So this part is for the unmined timestamp. So this is when that block ends. So what this does is that it takes the current time, whatever that current time is, as an integer. And let me show you what that's doing. So it's taking the second since 1970 and then getting the integer value of that. This is also called like seconds since the epoch. And then it's adding the increment, which is going to be 60. So like, let's say that you are at a particular time. All you do to find the end time of this block is to add 60 to that. And that's what's happening here. So when the blockchain is instantiated, the very first thing that happens is that we must create an on-mine block. And that's what this is doing. This is initializing the first block. So let's dive into that. So here, what it's doing is that it is getting a copy of the on-mine transactions. And the reason why you want to get a copy is because with Python, if you reference the actual list, you're going to be referring to that list in various places and modifying this in different functions. But we really just want a copy of that. So that's why we're taking a copy. And then here it's creating a block using all of those, all of the pre-existing information, such as the index, the copy of the transactions, the timestamp, and because this is the beginning, it's actually using the previous hash, which is none. And then once it does that, it will do it's going to create the it's going to reinstantiate the on-mine transactions as an empty array. All right. So let's go back to serve.py. So once you have your blockchain instantiated, then you can do various things with it within this web server. As I mentioned, scrolling down to on-mine transactions, you are able to get the current on-mine block. And there's one more thing that I want to show you actually in the blockchain code, which is really important. So in the very end, if I scroll down here, you'll see that you have the ability to run the blockchain. And what happens is that the blockchain is being run in its own thread. So there's a method called run blocking. And what this does is that this is just running. So while the blockchain is active, it's going to be running this code. Delay loop delays this so it's not being run too much, because if we only need to check this every couple of seconds or every 5 seconds, then we can slow this down, and that's what this is doing. Right now, this is slowing it down, so it's running every 0.1 of a second as a delay. And this is a pretty simple method, actually, very, very simple, but it's really important. So what's happening is that it's running every 0.1 seconds, and it's checking to see if the on-mine block has ended. If the on-mine block has ended, then it doesn't try to create another one. It just repeats the loop. And then there's another condition that it checks. So not only does it check to see if the on-mine block has ended, but also it checks to see if the on-mine block has been mined. So here, if the on-mine block has been mined, then it creates another one. Otherwise, if the on-mine block has not been mined, then what it does is that it repeats the loop. So something that I said before is actually not quite true. So I think I said that, actually I know that I said that once you have reached the end of that block, then all the transactions will go into the next block. Well, that's not quite true. What happens is, if you have let's say that you have a block and it has not been mined and it's just kind of sitting there, what's going to happen is all those transactions will be added to that block. So really, this system is really dependent on having miners mine. If miners don't mine, then these blocks will not get processed, and essentially you will have a bottleneck at like one block. I do have a solution for that, which is an auto mining system, which will be in another thread, but I've not created that yet. Anyhow, this loop is really important because this is something that's being run every 0.1 of a second. And it's not obvious if you're looking at the web server, but it is happening. Let me show you where it's happening. So we scroll here and you see how you have blockchain. So this instantiates a blockchain, and then this runs a blockchain. And you have that loop which is being running another thread. And then here in the web server, you have, those various endpoints. Right now, we really have on-mine block. And so I think you guys should have a good understanding of the process of obtaining a block which has been unmined. Now, the question is, when you have an unmined block, what do you do with it? Let's say that you wanted to mine a block. So that would happen with this particular piece of code. So let's say that you had the winning nonce. And again, a nonce is really just an integer. It's an integer that when you take the hash, which includes the blockchain information, that hash will be valid. And in order to understand that, we kind of have to dive into the code here. So here I have winning nonce is used to solve the unmined block. But what does that actually mean? So first step here is to get that information that's coming from the code that is submitting the winning nonce, and then you have the address. So this address is the public key of the user or account or the entity which is submitting the winning nonce. So let's say that I have my own computer and I have a public key, right? And I have this nonce that I believe or that I know is a winning nonce. I'm going to do a post request to this blockchain endpoint. And then here, this particular piece of code or method is going to take the winning nonce and then the address. If it's correct, then this address will be rewarded some token. And let's dive into it and see how that works. So this is mine block, a very important piece of code. And yeah, as I mentioned, the address is the address of the miner account, which is a public key. And then a nonce is the nonce or integer, which makes the hash valid. So the very first step is to compute the block hash. And I showed you guys that particular piece of code before that computes a block hash. Essentially takes the winning nonce, and then it takes a winning nonce, it takes the blockchain information, and then creates a hash of that. So that's all that's happening. And scrolling out here, and then here, this particular code at line 114 is deciding if this hash is valid. So let's take a look at how this works. So what this does is that the block hash is considered valid when it starts with 0. Do realize that the difficulty can be used to shift that 0. And the higher the difficulty, the harder it is to get a block hash which is valid. By the way, when the miner is determining that winning nonce, the miner does have access to the difficulty. That's something that the miner does know. So the difficulty has to match. If it doesn't match, then the miner will not be able to mine adequately. All right. So if the hash is deemed valid, then if it's deemed valid, then it continues. If it's not valid, then this function is going to return false, and as a result, the user will not get any token. And let me back out of this so you guys could see. Yeah, so if success is false, you're going to have false here, and the amount mined will stay 0. Let's go back up here. All right. If that hash is indeed valid, then what happens is the unmined block will get that particular hash, and then it's also going to get the winning nonce. So this is a nonce which causes the proof to be valid and work. And then that block is going to have the metadata be changed, so it has been mined set to true. This is important because it's going to block other miners from trying to mine the same block. And then after that, we will set the previous hash as the valid hash of the previous block, if it does exist. If it doesn't exist, then this particular code is skipped. And then update blockchain data. What this does is that this updates the flat files so that it will have the new blockchain data. So here it has insert new block. So that's being inserted into that flat DB. And then as far as the blockchain instance, it's going to actually append the new block. So this is something which is, so kind of taking a step back, what's happening is that it's storing persistent data and then it's storing non-persistent data. So the non-persistent data is this part. What do I mean? If you were to turn off this your blockchain, like just straight up turn it off, then this would just go away, because this is something that's only being kept by the web server. Now the persistent one is being kept in the flat file, right? So this is something that's being stored, and if you were to turn your blockchain instance back on, it is possible to start off with the latest block and then to start up the whole blockchain again. But yeah, so that information is being updated, and let's see. After that, we can then reset the information. So we can increment the index. So the next block that's being created is going to have the current index plus 1. Then also we can set the timestamp. So the next block will have a timestamp that's the same plus 60 seconds. And then this next line increases the amount for that particular user. So what it does is that it takes that address and then it assigns that particular user token. So this is essentially rewarding that particular user for mining that on-mine block. So this is the default, right? So by default, we're not going to add anything. And then what this does is that it gets access to that particular user's state as far as like how much amount this person has. And then what it does is that it increments that amount. So let's say that person had like 10 token. What it would do is that it would do the token plus whatever that amount is, which happens to be, so this is something that is arbitrarily set. So I said this is 1. What this means is that whenever a user mines a block, that user is going to receive 1. Now, I'm going to change this, by the way. So in the future, that amount is going to decrease. That makes this deflationary, which means that the longer, the higher the index, the less is rewarded. So that means that early miners will actually be incentivized because they're going to get more token. Let's say index were like 1 million. That means that you'll get a little bit less token. And this is done on purpose. Right now, that's not happening. But on my to-do, I will change it so it's going to be deflationary. All right, going back to this. So again, the point of this code is essentially to add token to the public key that did the mining. And then what this does is that this is updating the amount table so we can keep that persistent information. So we can say, okay, this person has received 1 token or X token. Let's make sure to hold on to this information within our flat DB. All right. Once that's done, then that's it. We have successfully verified that proof is correct, and then we have successfully added token to that public key that has done the mining. And going back out here, that is it as far as the mining process. So once that user has mined, that user will receive this information as the response. And I do have mining code here in the mining folder, so I'm going to jump into that real fast so you guys can kind of see how that works. And yeah, so the mining code is very simple, right? If you just run this file, it's going to run with these basic defaults. So it's using placeholder as your public key, which, by the way, is not a valid public key, but it kind of demonstrates the process and demonstrates how this works. Scrolling up here, what this tries to do is that this will create a mining instance and then run. And this is kind of similar to the blockchain instance, in which it's doing something every couple seconds or every some given time period, right? In this situation, we have I think I have 0.5 of a second as the delay. So that means every 0.5 seconds, this code is attempting to do a request. It's not actually attempting, it is doing a request. It is doing a GET request to get the unmined block. And then if that unmined block does exist, it is finding the winning nonce, and then it is doing a post request to mine, and then if it's the first one, it's going to be rewarded token. So that's exactly what's happening here. So kind of taking a step back, I think now you guys see how this works. Alrighty, so here we are. We're back to the README, and I want to scroll down and thank some creators that have come before me. So none of this would be possible unless I had access to these references. So what I did is I looked at many different tutorials about building blockchains in Python, and these were the best ones. So yeah, thank you, Active State and Geeks for Geeks. Very, very useful material. Now, if you guys have made it this far, you probably found this information interesting, and if you do like it, let me know. And also, I want to hear your feedback. I want to know what your thoughts are. Should we create another blockchain? Are there too many? Is this a bad idea? Is this a good idea? Let me know. I'm really curious. I want to engage you guys in a conversation about this. As far as next steps, as I mentioned before, this is missing the transaction component. So the next thing that I want to do, and I will do, is create some code that can process transactions. And yeah, that's what's next in the process. So until next time, take care of yourself.